Hello, this is Ryan Woodward recording for Intel's Digital Logic course. This is Lab 2, Part 5. And this part is a bit of an extension from the previous. Basically, what was required was to have the inputs of the 5-bit value be displayed on the 7-segment displays, but to also display the inputs X and Y, or A and B for the full adder, or the ripple carry adder out also on 7-segment displays. And it only mentioned that you had to do one 7-segment display per A and B. That might be because they wanted just 4-bit values, but I actually ended up using all 6 7-segment displays just to show the values independently. And another point that they mentioned was, rather than using case statements or a data flow, they suggested using if statements. And admittedly, I thought this was quite tedious. Similar to how I do the 7-segment decoder. To get 31, the biggest 5-bit value we can in this is really tedious. And since I know that part 6 is a 6-bit number that we have to send out to the 7-segment display, I will not be doing this case statement for 68 values. So that's not going to happen. I'm going to come up with a different way, code that better so it's more efficient and less tedious than that. Because eventually this is going to get quite heavy and tedious for our processor. But the full adder that I implemented for this is using a behavioral model, as you can see. And we're basically just checking and going through the truth table. That's what this is. And if A and B are certain values and carry in is a certain value, then we get that. So basically the sum should be 1 if A is high, or B is high, or Cin is high. And the C out should be high if 2 of the 3 outputs are high. And essentially that's what this circuit does. It's literally the same exact thing as the data flow model from the previous lab, but I implemented it in a behavioral model instead. The ripple carry adder, there's nothing different from this than previous labs, but this is it again just to show. The BCD 7-segment, as I showed, goes all the way to 31 now, and I will not be doing that again, but that's I'll be actually implementing it because it has to go to, I think, 68 for 6-bit numbers. So we won't be doing that again. But here is lab part 5. I made a mistake in my entity name. The top level entity is supposed to be lab 2 part 5, but I forgot the 2. And what you can see is that I actually have all 6 hex displays declared here in the port. And I have some extra hex displays, or actually have 6 hex displays that are intermediate values here. And instead of having them just be right in the BCD decoders, I decided to use the intermediate values just for the sake of me and organizing this a little more clearly in the code. So we can see that for BCD 0, this is the same as part 4, where we pass the sum to these 2 hex displays. BCD 1 handles if the input X, as you can see here. And I didn't do anything different. I just concatenated a 0 because this is going to be a 4-bit number always. It won't be greater than that. The sum is a 5-bit number. And so I concatenated a 0 so that it will stay in 4 bits. If I try to concatenate C out, it could give us a 5-bit number, and we don't want that because this is actually designed for 4 bits. These are 4-bit values going into a thing that handles 5 bits. I passed these out to 2 different hex displays for A, and then similarly below for Y, which is the B value in the switches A and B here. I pass out to hex 4 and 5. And that's it. It's just a bit of an extension. It's not really any different, but it does display the value of X, the value of Y, and the sum on the far right 7-segment displays. But that's it for the code, and here is a demo. All right, and this is lab 2 part 5. So we've got our input A or X on the far right, these 4 switches, then B, the second 4 switches, and carry in is our final switch. For the 7-segment displays, we have the sum, which is the far right 2 7-segment displays. We have A or X here, these 2 in the middle, then B or Y on the far left 2. All right, let's just start showing that we can actually show A and the sum change with the input of A. And I'll count up A to B, and then we'll just add them together. So we've got A, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 10, 11, 12, 13, 14, 15. There it goes. And then we can do B, 1, 2, 3, 4, 5, whoops, 6, 7, drop those 3 to get 8, 9, 10, 11, 12, 13, 14, and 15. All right, so we can see that we can change this value, the sum, with overall B, and B and A are reflecting properly on their own 7-segment displays. So let's just count up and we can watch it go to 31, 16, 17, 18, 19, 20, 21, 22, 23. You can see 8 there. 24, 25, 26, 27, 28, 29, 30. And where did we get 31? Our carry in. There we go. And that's it. Thank you.